Welcome back, friends. So let's see some more problems in the Laplace transform. Suppose if it is given like this, a waveform is given. For this waveform, I have to find what is the Laplace transform. For this x of t, I have to calculate x of s. How we can do that? First, we have to write the expression for x of t. So to write the expression for x of t, first we have to observe x of t. So it is having corner points as well as discontinuity points. So corner points are nothing but 0, 1 because there we are having the slope change, and the discontinuity point is nothing but 1 because there is a jump. So here let's say what is the slope of this line? 0. What is the slope of this line? 6. What is the slope of this line? 0. What is the jump in this line? That is minus 6. So according to this we can write x of t. X of t is equal to, at 0 there is a change in slope, 6 minus 0, 6 r of t, minus at 1 there is a change in slope, 0 minus 6, minus 6 r of t minus 1, and there is a jump, so minus 6 u of t minus 1. So this is what x of t. For this, what is x of s? 6 by s square minus 6 by s square with there is a shift, so e power minus s minus 6 by s e power minus s. So if you take s square, 6 minus 6 e power minus s by 6s. So this is what x of s. Take it. Next concept, Laplace transform of causal periodic signals. Causal periodic signals. Causal means which is existing only for positive values of. Suppose if I take a signal which is like this, x of t, so 0, t, 2t and so on. So this is a causal periodic signal which is existing only for positive values of light, and this keep on repeating. Then for this, what is x of s? What is x of s? That is x1 of s by 1 minus e power minus st. E power minus st. So here t we came to know that is nothing but period of the signal. Then what is x1 of s? So it is a Laplace transform of some signal x1 of t. Then what is that x1 of t? That is nothing but in the first period, whatever the signal we are having is nothing but x1 of t. If I know the signal x1 of t, if I know what is the x1 of s, then we can directly calculate what is x of s. Okay. Let's take one example for that. Zero, 1, 2, 3. Like this. 1. This is x of t. Now the signal what we are having in the first period is this one up to this point. This is what? X1 of t. So if I could find out what is x1 of s, then from that we can say directly what is the x of s. So here what is the period here? T is equal to 2. So you tell me what is x1 of t? We are having a jump u of t. We are having a downward jump minus u of t minus 1. So this is what x1 of t. So if it is x1 of t, then what is x1 of s? 1 by s minus 1 by s e power minus s. That means 1 minus e power minus s by s. So this is what x1 of s. So once we got x1 of s, from this we can calculate x of s. That is 1 minus e power minus s by s by 1 minus e power minus 2s. So this is 1 minus e power minus s by s into 1 minus e power minus 2s. So this is what x of s. Clear? Take it. A system and its inverse system. Both to be stable, which of the following is true? Option A. All the poles must lie on LHS, left half of S-plane, but zeros can be anywhere. Zeros can be anywhere. Option B. All zeros must lie on LHS, but poles can be anywhere. All poles and zeros can be anywhere. Option B. All poles and zeros must lie on left half of S-plane. Okay, listen here. A system and its inverse system. So how can we define a system and its inverse system? If they are cascaded, suppose a system with impulse response h of t is cascaded with its inverse system, hi of t. Then h of t convolution with hi of t has to be delta t. This condition has to be satisfied. Then only we can say it is an inverse system and it is invertible system. Now let's say if I take Laplace transform on both sides, then what will happen? H of s multiplied with hi of s is equal to 1. So from this can I say the inverse system having transfer function, what is nothing but 1 by h of s. This kind of inverse system we must have. Okay. So let h of s is equal to, let's say, s minus z by s minus p. Let's assume. So I can say this system is stable and inverse system is also stable. So if the system is stable, so here the pole is nothing but p has to be in the left half of its plane. That's okay. But from this, what is hi of s? Hi of s is equal to 1 by h of s, that is equal to s minus p by s minus z. We know that a system to be stable, their poles must be in the left half of its plane. So I can say for this system, pole is nothing but p has to be in the left half of its plane. For this system to be stable, the pole, here the pole is nothing but z. Z has to be in the left half of its plane. So from this I can conclude that both z and p has to be in the left half of its plane. Because for this system, that is inverse system, whatever the pole is nothing but zeros for the invertible system, original system, and whatever the zeros here, they are nothing but the poles here. So I can say this system to be stable, z has to be in the left half of its plane. This system to be stable, p has to be in the left half of its plane. So I can say all the poles and zeros has to be in the left half of its plane, so that I can say both system and its inverse system are stable. I hope you understood. So if p is in LHS, here z is in LHS. So I can say all the poles and zeros has to be in the left half of its plane. This is the condition. Clear? Take it. With this we have completed bilateral Laplace transform. Let's enter into unilateral Laplace transform now. Unilateral Laplace transform. So if x of t having unilateral Laplace transform x of s, then how we can define x of s, which is nothing but integral 0 to infinity x of t e power minus st dt. So this is what the unilateral Laplace transform. So here we are considering time only from 0 to infinity. That means we are neglecting the negative portion of time. So we are neglecting negative part of time. Negative time. We are neglecting t less than 0. We are neglecting x of t for t less than 0. That's what the meaning of it. What do you mean by that? Let's say, suppose if I give one example, u of t plus 4. For this one, what is the bilateral Laplace transform if I ask? The bilateral Laplace transform is equal to e power 4s by s. Now I want to find out unilateral Laplace transform. How we can do that? First, for this u of t plus 4, how it look like? This is what the signal. I told you in the unilateral Laplace transform we are neglecting x of t for t less than 0. That means we don't consider this part. We don't consider this part. Then this will be equal to u of t only. u of t only. So which is equal to u of t. For u of t, what is the Laplace transform? Unilateral Laplace transform. Unilateral Laplace transform is equal to 1 by s. 1 by s. That means next, let's see some more examples. U of t minus 3. U of t minus 3. So where it is existing? 3 to infinity. This is the signal what we got. Okay. For this signal, what is the bilateral Laplace transform? Bilateral Laplace transform is equal to e power minus 3s by s. What is the unilateral Laplace transform? That is also equal to e power minus 3s by s. So if you observe carefully, unilateral Laplace transform, bilateral Laplace transform are going to be same if the signal does not exist in the left half of, in the negative portion of time. So if the signal does not exist for negative portion of time, whatever the bilateral Laplace transform, that is going to be same as unilateral Laplace transform. Understood or not? So if x of t is equal to 0 for t less than 0, then bilateral Laplace transform is equal to unilateral Laplace transform. Clear or not? Take it. Next, suppose signal is a DC signal, x of t is equal to 1. How it look like? This is 1. Actually, for this signal, what is the bilateral Laplace transform? Bilateral Laplace transform does not exist. We have seen this. But for unilateral Laplace transform, we don't consider this negative portion. Then this is equal to u of t only. This signal will be equal to u of t only. For u of t, what is the unilateral Laplace transform? That is equal to 1 by s. That's why whenever some people will ask what is the Laplace transform for 1, directly they will say 1 by s. But remember that 1 by s is a unilateral Laplace transform, but not the bilateral Laplace transform. Clear? Take it. In the similar manner, suppose if I take x of t is equal to signum t. Signum t. For this function also, bilateral Laplace transform does not exist. Does not exist. Then what is the unilateral Laplace transform? If I don't take this negative portion, then this is equal to so this is u of t. So for this also, unilateral Laplace transform is equal to 1 by s. 1 by s. Okay. So here one very important property, which is differentiation property. Differentiation property. What is the differentiation property? See here, if a signal x of t having x of s, here we don't talk about the ROC concept, because whatever may be the signal, somewhat ROC is always existing, so we don't worry about ROC here. Okay. So differentiation property, let's see, dx of t by dt is having Laplace transform, which is s x of s minus x of 0 minus x of 0 minus. That is nothing but the initial value. Next, in the similar way, second order differentiation, having s square x of s minus s x of 0 minus x dash 0 minus, where what is x of 0 minus, which is nothing but x of t when t is equal to 0 minus. X dash of 0 minus is nothing but dx of t by dt when t is equal to 0 minus. Understood or not? So this is what it means. Take it. A continuous time LTI system is described by y dot t plus phi y of t is equal to u of t, where u of t is a step function. If small y of 0 is equal to 1, then y of t is options 0.2 plus 0.8 e power minus 5t, option B 0.8 minus 0.2 e power minus 5t, point 0.8 plus 0.2 e power minus 5t, 1 minus e power. Okay, so they have given y of t, they want to find out y of t differential equation. Y dot of t means it is a dy by dt. Okay, so here they have given dy of t by dt plus 5y of t is equal to u of t, and they have given initial conditions. That initial conditions means it is a unilateral Laplace transform. So if it is a unilateral Laplace transform, suppose if I take a Laplace transform on both sides, then this is going to be s y of s minus y of 0 plus 5y of s is equal to 1 by s. That implies s plus 5 y of s. What is y of 0 which is given? 1 is equal to 1 by s. So that implies s plus 5 into y of s is equal to 1 plus 1 by s, that is s plus 1 by s. So from this y of s is equal to s plus 1 by s into s plus 5, s into s plus 5. This is y of s. So from this y of s, we have to calculate y of t. For that, first we have to do the partial fractions. So cover up method, if I take s is equal to 0 here, then it is going to be 1 by 5. 1 by 5 by s. Next, if I take s plus 5 cover up method, so this is going to be minus 5 plus 1 by minus 5, that is 4 by 5 plus 4 by 5 by s plus 5. Okay, so what is y of t then? This is 1 by 5, that is nothing but 0.2, plus this is 4 by 5, that is 0.8 e power minus 5t u of t. That is what answer. But here they haven't given y of t, but still it is a correct answer. Why? Because it is a unilateral Laplace transform. Even though if it is not given u of t, still we can say it is existing only for positive values of time. So which is the correct answer? This. Check it. Initial value theorem, final value theorem. Okay. So try to understand. First, let's see initial value theorem. Initial value theorem talks about initial value. That means, suppose if I know x of t signal, what is the initial value? When you substitute 0, but not exactly 0, it is 0 plus. Initial value means 0 plus. So x of 0 plus is called as initial value. So if you know x of t, that means we have to put t is equal to 0 plus, then we can get initial value. But what is the initial value theorem is saying that instead of knowing x of t, if I know x of s, still I can calculate the initial value. That means without knowing x of t, if I know x of s, still I can calculate initial value. How we can do that? That is equal to limit s tends to infinity s x of s. S x of s. This is what the initial value theorem. Next, what is the final value theorem? That is x of infinity. That means when x of t is known, if you place t is equal to infinity, then that is nothing but the final value. So in the final value theorem, it is saying that limit s tends to infinity, s tends to 0, not infinity, s x of s. So to know at 0, we have to place s tends to infinity. To know at infinity, we have to take s tends to 0. So these are the formulas. But it is not that simple. That means these theorems may be applicable, may not be applicable. So it's all depending on some conditions. Let's see what are those conditions. Conditions. For initial value theorem, for final value theorem. What are the conditions we are having? Let's see. First condition in initial value theorem is x of t must be causal. Must be causal. Here also the same. X of t must be causal. Next, second point in the initial value theorem, x of s, that is something like p of s by q of s. So must be proper fraction. Must be proper fraction. What do you mean by proper fraction? Degree of denominator must be greater than the degree of numerator. Then we can call that is a proper fraction. That is degree of denominator is greater than degree of numerator. If this condition is satisfied, then we can call this is a proper fraction. So to apply the initial value theorem, that means to apply these formulas, we must check these two conditions. If these two conditions are satisfied, then only we have to apply it. Next, what is the final value theorem? Next, second condition in the final value theorem is there should not be any pole on RHS, right half of S plane. So in the right half of S plane there should not be any pole, and on imaginary axis, on imaginary axis. So on the imaginary axis also there should not be any pole. On the right half of S plane also there should not be any pole. But one pole at origin is allowed. So, but one pole at origin is allowed. These are the conditions to apply the final value theorem. Okay, take it. Let's take one example. X of S is equal to 1 by S, 2 by S plus 1 by S plus. For this we have to calculate initial value and final value. So let's see method 1. This method 1 is always true. That means we don't have to check any conditions here. Directly we can calculate initial value and final value. What is that method? Find x of t. If you place t is equal to 0 plus and t tends to infinity, you can get directly initial value and final value. So method 1, so always applicable. Always applicable. So what is that? First find x of t. What is x of t? 2 plus e power minus 3t u of t, because it has to be causal signal, so I have taken causal signal. Okay, so now you tell me what is initial value. X of 0 plus, that is 2 plus e power 3 0 plus u of 0 plus. So this is 2 plus 1 into 1, that is 3. Final value. X of infinity, that is 2 plus e power minus 3 into infinity u of infinity, 2 into 1, that is 2. So this is the final value. Okay, let's see method 2, that means initial value theorem, final value theorem. So if I apply initial value theorem, final value theorem, so first we have to see what is x of s, if it is satisfying both the conditions or not. Okay, method 2. In method 2, what is x of s? Which is 2 by s plus 1 by s plus 3, that is 2 into s plus 3 plus s by s into s plus 3. That is 3s plus 6 by s into s plus 3. So first, is it a proper fraction? Yes, definitely it is a proper fraction. Next, is it having any pole on the right half of its plane? No. What are the poles actually? 0, minus 3. So poles are like this, 0, minus 3. One pole at origin is allowed and every pole is on the left half of its plane. So this is also valid. So we can apply initial value theorem and final value theorem. So if I apply initial value theorem, then what is x of 0 plus, which is limit s tends to infinity s x of s into 3s plus 6 by s into s plus 3. S get cancelled. Never substitute infinity directly. Always substitute infinity in the form of 1 by infinity. Then what it is going to be? Limit s tends to infinity 3 plus 6 by s if you take common out 1 plus 3 by s get cancelled, common out ends. Then this is 3 by 1, which is 3, which is what we got initial value. Next, final value theorem, that is x of infinity limit s tends to 0 s into 3s plus 6 by s into s plus 3. S get cancelled. If I substitute s is equal to 0, that is 6 by 3, which is equal to 2. Yes, this is also valid answer, final value. Okay, I hope you understood how to apply initial value theorem and final value theorem. Take it. Example. Find final value of x of t if x of s is given like this, 2 by s square plus 4. 2 by s square plus 4. So they want to calculate final value. So without observing the conditions, if I go for final value theorem, let's say final value theorem. So in the final value theorem, x of infinity is equal to limit s tends to 0 s x of s, that is 2 by s square plus 4. So if I substitute s is equal to 0, this is going to be 0. Now this answer is a wrong answer. This is wrong. Why? Why it is a wrong answer? Let's see. First of all, final value theorem is not applicable. Why, sir? So if you observe carefully, what are the poles we are having? Poles is equal to s is equal to plus or minus j2. Plus or minus j2 means they are here. j2 minus j2. So they are on the imaginary axis. I told you, whenever poles on the imaginary axis, final value theorem is not applicable. Final value theorem is not applicable. Final value theorem is not applicable. That doesn't mean that we cannot find the final value. Yes, we can calculate the final value. How? Then we have to go for x of t. What is x of t here? X of t is equal to sine 2t. Sine 2t. How it look like? Sine 2t. Okay. Minus 1 plus 1. So we are having oscillations, that too up to infinity also we are having oscillations only. So if we are having oscillations only, so u of t. So we are having oscillations only. At infinity also we are having oscillations. That means we cannot say certainly what is the value. but we can say only one thing, its value may be which is between -1 and +1, any value between -1 and +1. So x of infinity is undetermined, that is any value between -1 and +1. It can be any value between -1 and +1. We cannot say certainly what is the value. Clear or not? This is one example. Let's take one more example. Find final value of x of s, x of t if x of s is equal to 1 by s minus 3. Here also, if I directly go with the final value theorem, so x of infinity is equal to limit s tends to 0 s x of s. So this is limit s tends to 0 s into 1 by s minus 3. So finally this is going to be 0. This answer is also wrong answer. Why? Because if I observe what is the pole here, s is equal to 3. So which is on the right half of s plane, which is on the right half of s plane. So final value theorem is not applicable. Is not applicable. If final value theorem is not applicable, then what we can do? We can go for x of t. What is x of t? E power 3t u of t. E power 3t u of t. So in this directly if I substitute x of infinity, e power 3 into infinity u of infinity, that is going to be infinity. This is the correct answer because it is a growing exponential, right? So if it is a growing exponential whose value at t is equal to infinity is infinity. Clear? So be careful while we are applying the initial value theorem and final value theorem. First we have to check the conditions. If the conditions are satisfied, then only we have to apply the initial value theorem and final value theorem. If conditions are not satisfied, still we can calculate initial value and final value, but we have to calculate x of t. If I know x of t, then only we can say what is x of 0 plus and what is x of infinity values. I hope you understood. Take it. With this we can conclude Laplace transform. From next session onwards we can start with the Z transform.